Hello everyone, welcome to the fifth lecture on machine learning with financial applications. So in this video, we're going to talk about the logistic regression, which is another type of widely used linear type of models. So let's get started. Let's look at the last lecture on linear regression. Right, so linear regression is in the form of y equals to beta 0 plus beta 1 x1 plus beta 2 x2. So let's just say we have two independent variables, or called predictors, and then have the target y. So we know that this is a linear regression, so that the target variable y is a continuous variable, right? So it takes numeric values that is within a certain range. Now, the downside of this model is that it is actually not easy to control the variable, the target variable. So say we have a application where the target needs to be only 0 or 1, right? 0 can be fraudulent transaction or normal transactions. This is a scam. This is scam email or non-scam. So there are many applications where we need the target variable y to take the value of 0 or 1, right? So, but with the tools we have, which is linear regression, how can we do that? So one way is to say, let's just say we have another threshold, right? Threshold which we define in advance. So we can have a ad hoc rule. So we have prediction y hats, right? And so say if y hat is threshold t, if y hat is less than t, then we make it 0, right? Else we make it 1. So that's just an ad hoc rule that can transform the original prediction to a binary value, right? Whether it's 0 or 1. The problem is that now this threshold t is very difficult to choose, and it is domain dependent, meaning each application, each dataset will have its own threshold, and it is easy to pick the threshold based on without knowing the data itself, right? So what we can do, however, is to use something called logistic regression, and let's see how it's done. So logistic regression model is a model that's actually used to model the binary outcome. So which means when the variable target variable is binary itself. So in other words, we have the y belonging to either 0 or 1, right? It can only take the value of 0 or 1. And there are some process we can use to model it. For example, we can see that it follows y follows a binomial distribution binom, right, with certain probability p. So what this means is that with probability p, which is a number between 0 and 1, because it's probability. With probability p, I have success, right? And 1 minus p have failure. So, so what this means is that, let me just change it here because it should be a Bernoulli distribution. So about that, Bernoulli distribution. So what Bernoulli distribution says that for a binary outcome, my success rate, my success probability is p, and my failure probability is 1 minus p, right? So it can only take on these two values, and the probability of taking on the value of p of y equals to 1. Right, so y equals to 1 is probability p, equal to 0 is probability 1 minus p. So that's what Bernoulli distribution says, and that's what we're going to use to model the outcome y, right? So that's from a data generating perspective. Let's back to our linear regression case. So originally we have y or y hat, more specifically, equals to beta 0 plus beta 1 x1 plus beta 2 x2, right? So how do we transform it to a number that's between between 0 and 1, right? So that's what something I want to do. So I want this number to become a number that's between 0 and 1, so that we are actually modeling, in this case, we are modeling the probability of being 1, right? So this is probability of y equals to 1, right? So we can change the notation here. So let's just say this is z, right? This is still our linear regression, but now we use z to indicate that this is the result of linear regression output, and this z needs to be somehow connected to be able to tell me what is the probability that y equals to 1. In other words, probability of y equals to 1, right? If I have the probability, then I can, based on probability, and know that how much of likelihood it will be 1, how much likelihood it's 0, right? So this is a change of the problem definition that's defined by the logistic regression, right? So the question is, how do we go from Z to P? Okay, so the way we do this is through something called a sigmoid function, right? Sigmoid function, which graphically looks like this. So it's going to be an S curve, right? S curve, and let's just look at the input and output. So input is Z. Z can be any range, right? It can be negative infinity to positive infinity. So that's matches our expectation for a variable being continuous, right? So it can vary. However, for each input Z, we're going to project it to the corresponding value here, right? So this is every point we're going to project this curve to the corresponding P. So P here in this case, it can only range from this maximum 1, this is the lowest 0, right? So this function has a limit, upper limit 1, lower limit 0. So it's bounded by 0 and 1. But that means the output is going to be between 0 and 1, right? So we have input Z going inside can take on any value, output P, which is probability that's falling between 0 and 1, right? So what's the definition? What's the form of the function? It looks like this. Right? So equals to 1 over 1 plus e to the power of negative z, right? So that's just the definition of function. We don't need to know how this function is exactly constructed. We just need to know that this function, called sigma function, helps us to transform z to p, a probability between 0 and 1. And we can use this function for any other variables, as long as we want to shrink the input variable to a value between 0 and 1, right? So now things become better, because now we can still do the linear regression, right? This is step 1, to calculate Z, which is intermediary outputs, right, from linear regression. And step 2 is to convert it to a probability score, right? And this is our output, right? So P is our output. In this case, our y hat is P here, right? So our y hat, which is the output prediction, is the P here. So in other words, when we are using logistic regression to do prediction, we are predicting the probability, right? The probability of y being equal to 1, right? It's simply a number between 0 and 1, because it is probability, and this probability says that I'm going to predict, and I'm going to predict the likelihood. That's why we're taking on the value of 1, right? Of course, you'll be asking, oh, it's still not 0 or 1, right? We can have a third step, which is that, oh, now let's have another threshold t. So this is where we choose t. So if p is less than t, then y hat equal to 0, else, or which means p bigger than or equal to t, then we can make it 1, right? So this t is now easier to choose, because it is always going to be between 0 and 1, right? So now we can still introduce t, which is so-called user-defined hyperparameter, but now we can get exact at least 0 or 1 from the original probability, right? So we are predicting probability, but we can use additional step to convert the probability to a binary score, right? Okay, so as usual, we looked at the prediction function as a component of the whole model training process. And according to our first lecture, there are different components, the 4 components: the data, the prediction function, the cost function, and the optimization. In this course, we're going to mostly cover the prediction function, and of course the data, and the cost function, right? So, or sometimes called the loss function. But we're going to leave optimization because it involves more advanced discussion, right? So, cost function or loss function lets the model gauge how good or how bad the current prediction is, right? So we have a target y, which is 0 or 1, right? It's gonna be 0 or 1, and we have y hat, which is the number between 0 and 1, right? This means that y hat is a probability and y is a binary value, either it's 0 or 1, right? A linear regression, we can just take the difference square and then sum it up, right? For all the individual instances, I from 1 to n data points, and then take average. So this is how we calculate the mean square error. It's our cost function, as our loss function, and then we can use that to guide the optimization process for the model, right? So we want to minimize. This is something we want to minimize. However, in the logistics question, we cannot do this because now if we plug in y hat and yi, so y is going to be only 1 or 0, and y hat is going to be the number between 0 and 1. So it's actually a bounded, right? So there's not too much of a differentiation between small error and big error, and this is in fact a not so sensitive metric. So we want a cost metric. We want a loss function that is sensitive to the errors, right? So we want it to be able to tell this is small error, this is big error. So that's the reason why we're going to find another better metric, right? So the loss function we typically use is so-called coarse entropy loss. Coarse entropy loss. In this case, we're doing binary prediction, binary classification. So it's called binary case. Of course, we have a more general multi-category case, right? So in the binary loss function, the loss between 2 variables, between 2 quantities, y and y hat, is assuming this form. So we're going to calculate y times log of y hat, and then plus y minus y, which is the opposite side of things, log 1 minus y hat, right? And then this quantity, we're going to sum it up, then take the negative. So that's how we calculate this number. And of course, we can analyze a bit. So this quantity, so what is y hat? Y hat is a number that's between 0 and 1, right? Which means so this is a range that can vary because it's a probability. Now we look at the logarithm function. So the logarithm function looks like this. This is, for example, this x, this is y, and this is y equals to log of x. And this is y. So when x is between x and 0 and 1, which is this range, y will always be negative, right? Always be negative when x is between 0 and 1. Right, so this is negative number, which means this is negative. Also, this is negative, right? So that's good because now we identify the sign. Y and y minus y will always be positive, right? So it's gonna be positive, or 0, right? So let's just say positive 0, positive 0. So this will be negative or 0. This will be negative or 0. And of course, we have negative sign. So that's why we have a negative sign here, because we want it to be a positive number. So cost needs to be positive, so that we again minimize it, right? Because it's cost. So that's why I have negative sign here. That's fine. And secondly, let's just plug in a few different cases. So if the true label of y is equal to 1, right, our loss becomes something like this. So it's going to become negative log y hat, right? Because when y equals to 1, so this will be 0. And because 0, then we can ignore its term, right? So this becomes 1. And second case is if y equal to 0, then we're going to focus on the other side. So loss will be, so this is 0, this becomes 1. So this will go away. So only have negative log 1 minus y hat, right? Y hat is our probability again. So that's what we have, and basically this is a typical way we combine two different cases. So originally we have two cases, and now this isn't just one formula, which is the coarse entropy loss. We combine these two cases together. So that's just a nice mathematical trick. But this is to be able to analyze a function, we need to separate into two different cases, the 1 and 2, two cases. So so now we have a host of the loss function, and we can analyze so into two cases. So if that's the case, right? So if for the first case, we can again separate into two cases, 1 and 2. So if y hat is close to 1, right? What does that mean? So my true label target is 1, and my predicted probability of being 1 is close to 1. So let me see, it's a very good prediction. So I wish the loss should be very small, right? Is that case? So let's look at so when the function, so when y hat close to 1, meaning back to this graph, y hat close to 1, so this will be very close to 0, right? So if it's going to be close to 0 means it's going to be very small, right? Loss very small. So that's what we expect. If y hat is close to 0, because it can only go to 1 or 0, right? In the extreme case, we expect the loss is very big, right? And is that the case? So when y hat goes to 0, means that in this curve, I'm going to the value is going to be very negative, right? And taking the opposites, so it's going to be very positive. So it's going to be a very positive, very big number. So which means the loss is going to be very big, right? Which matches our intuition about or expectation about the loss. So in the far off prediction, the higher the loss. The closer the prediction, the lower the loss, right? So that's matches our expectation. Similarly, we can do the same analysis for the second case, which are not still, right? So but this is the way we analyze the design of the loss function. All right, so talk about the sigmoid function, and just ignore it. In this case, I'll talk about the odds. So the odds is defined. It's just another way to describe probability, but in this case, we have sort of the relative probability, right? Relative ratio in terms of probability, right? So the odds is just another way to describe the likelihood, the probability, but in terms of the ratio between the probabilities. So in this case, I have P, I have 1 as P. Again, P equals to the probability, the predicted probability of being y equals to 1, right? So let me just expand it out. So P by definition is 1 over e to the power of minus z. So again, just remind you, z equals to our usual linear regression here. And we're going to use, just going to use the sigmoid function to transform z into a probability score P, right? And then bottom part, we have 1 minus this guy, right? So so we can do the usual math, and then it will cancel out, which it will, and then it will be e to the power of z. Right? So this is what we mean by the odds. So we can again calculate z and then just take it to the power of z using the exponential base, right? E to e base e, and then we can calculate the odds. So There's another term called log odds, which is quite often. Log is just to take the logarithm, so we have z, right? So in other words, log odds is just z, which is our output of linear regression. And this one is also quite widely used because we have a name for the output here, right? So previously we called it intermediary output, but now it's actually the log odds, right? So also, if we know p, right, and we know how to calculate the odds, 1/1 minus p, and we all know how to calculate the log odds, you just take the log, right? So this is something we can calculate if we know p, right? So we can calculate backwards, and then gradually gets. So this is again defined as the z, right? So we can calculate from p to z. So this is from p to z, and also go from z to b, which is plug in the definition, right? Okay, so odds ratio is just a tool for us to analyze the impact of a certain input xi to the output y hat, right? So in this case, the output is not really the right, but it's called the odds ratio of the y hat. So odds ratio. Let's see how it's defined. So it's defined as two cases. So first case we have if it is a binary input, right? So let's just simplify the case. If it's binary, then xi will be either 1 or 0, right? So this is two cases. So for the two case, for this one, I have I can calculate probability of p equals to 1, right? Y equals to 1. So I have one probability, and I can calculate the odds, which is what we have, right? So this is one odds. We have another odds, which is when x equals 0. Then I can also calculate the probability, right? I have another probability which I call p0, which again is used to measure the probability of y equals to 1. So this is another odds, which is above z, maybe another z. So it's not okay. So I have two odds. So this is odds 1, this is odds 2. I want to take the ratio, so because it's called odds ratio. So I have p1 minus p1. This is first odds divided by the second odds, and this is again maybe just let's say above z, still keep it. But this is z when xi equal to 1, when xi equal to 0. So by definition, we can plug in, right? So e to the power, so z is equal to beta 0 plus beta 1 x1. Let's just say it's x1, right? x1 plus beta 2 x2. Right? So we can plug in, which will be beta 0 plus, because x1 is equal to 1 now, beta 1 plus beta 2 x2. Right? Then over e to the power of beta 0. And this, because x1 is 0, then it's going to be beta 2 x2, right? So then we can plug in, and we know that it's going to be e to the power of beta 1, right? So which means if my xi, right, shifts from 0 to 1, right, changes from 0 to 1, this will be the change to the odds ratio, right? So this is change to the odds ratio of y equal of the probability of y equals to 1. So this is just another way to quantify the impact, like how much I change x inputs and it changes my output y hat, right? So this is just one way to quantify, and it is through the lens of odds ratio, right? And we can calculate it because it just follows the definition of the odds. So first get the odds and then get the odds ratio, and then this term will extract. So this quantifies the impact of x to y in terms of odds ratio. All right. So lastly, we have the different accuracy metrics. So again, we talk about accuracy, but we have not defined it. So usually we use something called confusion metrics. And this is just a matrix that widely used to quantify the performance of the model. So assume we have a true target, true label, right? So this is our rows. Column-wise, we have the predictions spread, right? So now we have a table. So true label, it can be either 0 or 1. Prediction can also be either 0 or 1, right? So this gives us a label, a table with this a few numbers. Okay, so it should be here. Let's just say this is ABCD. Right, each number represents the number of instances that falls into this cell, right? So A means that my true label is 0 and my predict is 0, so it's good prediction, right? This bad prediction, and good prediction. So accuracy is defined as the total correct predictions, which is A plus D, times the divided by the total instances, right? Instances. So in this case, it's A, B, C, D, right? So this is just the definition of the accuracy, which is overall. But sometimes we want to look at from the accuracy from different angles. So there's something called recall. Recall is just saying that out of all the true labels, that is 1, right? So what is the correct predictions? So what is how much of my true ones are being correctly predicted, right? So let's just define. So I need to get the total true, the total instances. Well, the label is 1, right? So you can say that is C plus D because it's this row, right? So we have C plus D number of instances, observations that have Y equal to 1, the true label equal to 1. So out of this group, how many are correctly predicted, right? Correctly is this guy, so it's D here. So this gives us a ratio in terms of how much of a recall, right? How much can I recall from the true ones, right? So that's about that's what angle. Another metric which is common is called precision. So precision is to say out of all the predictions of all the predicted ones, how many are real, right? This is just another angle to look at the algorithm. So how much of the how much of the predicted ones? So what is predicted ones? To predict ones is this one, right? So we look at prediction 1, and we look at how many are predicted as ones, which is B plus D. Now, what is the correct predictions, which is again still D, right? So this is another angle, which is quite useful. And typically, this is a trade-off. So as we improve the recall, then precision will drop. As we improve prediction, recall will drop. So how do you choose? There's something called the RC curve, which will help us to determine. But again, this involves the notion of our threshold, which we mentioned earlier. But this threshold so once we choose a threshold, now we can determine the number of counts for each cell, right? Because now our prediction is again still a probability. So y hat is a probability, and we need to go through this threshold to get the table. And this table tells us what is the accuracy, what is the required prediction. As we vary, so this one changes, then the table will change. Then the accuracy recall prediction also changes. So choosing the threshold becomes more of a domain-based decision, right? So when you look at the domain, is it high stake, right? If it's high stake, then you probably want to have a lower threshold so that you highlight those potential suspects. But if it's not, so the downside of highlighting those small probability suspects is that you will have many false positives, right? Because as long as it's above some threshold, then you highlight, but this will increase the false positives. So again, this is a threshold that's depending on the domain itself. All right, so that's it for this video, and thanks for watching. I hope to see you in the next video.